My polar bears and polar cubs, welcome to remote learning. It's chapter 6. Let's talk about what happens with a bond. So, what happens with a bond is you get two electrons that are pulled from both nuclei, and it creates a chemical bond. As you can see, it overlaps right there. So, there are two types of bonds that we're going to talk about more in depth. There are actually three types of bonds. The first type of bond that we're going to talk about is an ionic bond. So, with an ionic bond, you have what are considered takers and givers. So, what happens is electrons get transferred. So, a metal will become a cation, and a non-metal becomes an anion. Anion being negative, they're getting an extra electron, becoming negative. Cation becoming positive because they're giving up one. With covalent, they share electrons. The big thing that we want to know about covalence is these are two nonmetals. So when you identify a type of bond, ionic, if you find a metal and a nonmetal, it is ionic. If you find two nonmetals, it's automatically covalent. Then we're going to break it down. So covalent has two subgroups. It has a nonpolar covalent and a polar covalent. So nonpolar means that they are equally sharing of the electrons. So the electrons will spend equal amount of time with each atom. Polar means that there's unequal, meaning they're going to spend more time around one than the other. I always say this is kind of like having divorced parents who have a agreement that maybe you go see them every other weekend, but you don't really see them during the week. Do you spend time with both? Yes. Is it equal? No. And then finally, really the only one that happens between metals themselves is metallic. This really, we just want you to understand that metallic bonds are what allows us to have electronics and things like that, and allows electricity to flow through. So, ionic, it must be a metal plus a nonmetal. If it's two nonmetals, it's automatically covalent. So I want you to understand that this chart below is correct, but it has some nuances to it. So, what do I mean? So, ionic is automatically a metal plus non-metal. However, you can have an ionic bond between a metal and a non-metal that doesn't reach the 1.7 threshold when it comes to electronegativity difference. That also being said, with polar covalent, which is a non-metal plus another non-metal, you can have that which actually goes above the 1.7 electronegativity difference, but it's still polar covalent. So I want you to understand that as long as it's two nonmetals, as soon as it becomes greater than 0.3, it's polar covalent. And as long as it's a metal plus a nonmetal, it is ionic. So, how do we show these bonds? Okay, with ionic bonds, we show them with arrows. We show this transferring of electrons from one to the other using arrows. So, if an atom gains electrons, it's called an anion, which now has a negative charge. If it loses, it becomes positive. So, how did I get this electronegativity difference of 2.1? Well, on your periodic table, chlorine has an electronegativity of 3.00. Sodium has a electronegativity difference of 0.93. So when you subtract that, you're going to get actually 2.07, which would round up to about 2.1. Where is electronegativity found on your periodic table? That is in the upper right-hand corner. And then would it be considered a ionic bond? Yes, because sodium being a metal, chlorine being a nonmetal, they would bond together ionically. All right, so the next thing is a covalent bond. The covalent bonds we would show kind of like this. What happens is you might have electrons that bond. We're going to show by circling, saying that they are shared. And they go between both. So nonmetals, they are found on the right-hand side of the periodic table, the right-hand side of the stair steps. How do you determine the difference? Well, if it is two of the same, the difference will always be 0. So with this, it'd be 3.00 minus 3.00, giving us 0. So because it is below, or it's in our range of 0 to 0.29, it is nonpolar covalent. So as this, you can see that it comes together. They overlap. So they are sharing them, which makes it covalent. On the other side, you see the arrow for transferring, and that makes them ionic. Ions are formed in ionic bonds. So right now would be the good time for you to write down the electronegativity difference and what the electrons do. Give you 3, 2, and 1. So the electronegativity difference is 1.7 and greater. Polar covalent is between 0.3 and 1.69. These are shared. Same thing here. And this is a transfer. Nonpolar would be 0 to 0.29. Those are handy differences to know. So this is a lot about showing how we might draw the bonds or the elements together if they're the same. But I want to talk to you about like carbon dioxide, for example, and how I come about this drawing. So carbon has 4 valence electrons. Oxygen has 6. We'll put another oxygen here. Now, when you add those up, 6 plus 6 is 12, plus 4 is 16. So I have 16 dots there. That means that when I make my drawing, I'm only allowed to have 16 dots. So what normally happens is you would go like this, and you'll bond them. Now, they've bonded together, and you could draw this like so. Now, if I count, I still have my 16. However, they're not satisfied because not everybody has 8. And we'll talk about that in a little bit. Octet rule. What happens is they need to bond again because those lines that are shown equal 2. And that's how we get this kind of drawing for CO2, because we're trying to make sure that everybody is satisfied by the octet rule, but also we stick to the number of valence electrons that we have. So first thing you want to do is you want to work through the difference. So this one, I know that the difference is about 3.1. It's going to be ionic. It's ionic also because this is a metal and a non-metal, which means that it's transferring. With H and O, H is a non-metal. So I want you to remember that H is a non-metal. So the difference there is 1.3. This puts it as polar covalent, or PC, and they are shared. All right, I'm going to have you guys work on that, and then we'll go through the answers here shortly. 3, 2, and 1. Anytime that you have two of the same elements bonded together, it's a 0, making it NPC, and they are also going to be shared. C and O, the difference there is 1, which makes it polar covalent, which means that it is also shared. K and Br, I know instantly that because K is a metal and Br is a non-metal, that this is going to be transferred. It is ionic. And now for the difference, Br is 2.8, K is about 0.82, so that makes it 1.98. Finally, hydrogen, again, non-metal, chlorine, non-metal. The difference is 0.8, which puts it as polar covalent and puts it as sharing. So, I hope that you did well on those. Moving forward, Lewis dots, I do the dots for both. You can do the X's and the dots, that's fine. It is a way that you can kind of see it, and you can see which ones were transferred in and which ones were not. Covalent, we're going to circle one dot from each of the elements. Okay, our octet rule. The octet rule comes from the main group elements, so that is the S and the P group. And with those, you only have 8 electrons. The exceptions to those would be hydrogen and helium, which only want 2. Boron only wants 6. And beryllium only wants 2 as well. 4, I'm sorry, when it bonds. Now, something else to let you know, that the reason that beryllium wants 4 valence electrons is this acts covalently. So, although beryllium is a metal, it is the only metal that bonds covalently. So, drawing carbon has 4 valence electrons, so we're going to have a dot on each side. Oxygen, again, I don't specify which way you need to do it, but if you start at the top and go clockwise, doing 1 on each side first, and then going back until you run out, that works fine by me. Magnesium has 2. Boron has 3. And beryllium has 2. So that's some part of it. There are 7 diatomics. What's a diatomic? Well, a diatomic are things, they're atoms, they're elements actually, that are found in pairs of atoms in nature. So they are hydrogen, chlorine, nitrogen, bromine, oxygen, iodine, and fluorine. So if you're looking at your periodic table, if you find nitrogen and you go over to fluorine, there's your top. And if you take fluorine down to iodine, there's your side. And it looks like a 7. Well, there's 7 of them, but there's only 6 that make up the 7. The tricky one is hydrogen. I always nicknamed these the pesky 7 because they always kind of they always pop up when you need them least. Okay. And they always kind of make life a little rough. So I would recommend that you memorize these 7 so that it doesn't trip you up moving forward. All right, so let's show some ionic bonds. So K only has one valence electron. Fluorine has 7. So you're going to draw K with 1, fluorine with 7. You'll show that K transfers that 1 to F. And then what we'd like to do is we like to show them as charged particles. So because K lost an electron, it became +1. Fluorine gained 1 electron, so it became -1. Okay, so this can actually go down here. Now, what happens? Let's do another ionic one. With this, magnesium has 2, iodine has 7. So if I'd show this, well, magnesium still has another I, or another electron. So it needs another I in order to transfer that electron. So what ends up happening is you draw another I. That gets it. So then when we draw it out, you have I with all 8 electrons becoming negative. You put Mg in the middle. It is now a +2 because it lost 2 electrons. And you put I on the other side as a -1. All right, let's try some covalently bonded molecules. So this will draw out both fluorines with the proper number of valence electrons. Then you actually circle the ones that would be shared. And then your final drawing would be, you still have to show all electrons that are pairs. The line would then represent the bonded pair. And when you count them, it goes 2, 4, 6. This is 8, 10, 12, and 14, which is the correct number of valence electrons. Here, how did I get that 14, by the way? It is 7 plus 7, giving you 14. Moving on to number 2, you have 4 plus 6, giving you 10. Now, this one can be a little tricky, and here's why it's a little tricky. So if I draw out carbon and I draw out oxygen, I have 10 valence electrons, but they need to have a grand total of 8. They need to feel like they're sharing 8. So the first thing that I'm going to do is I'm going to bond them, and then I'm going to make sure that everybody else is full, making them 8. Then I'll count. So 2, 4, 6, 8, 10, 12, 14. I'm at 14. So this drawing has 14. I'm only allowed to have 10. So this drawing can't be right. Well, what do you do to reduce the number of electrons shown, but get closer to your right drawing? These and these are going to get crossed out. And what will happen is they get replaced by a additional bond in between the C and the O. And then we'll count again. So remember, this one is wrong. So 2, 4, 6, 8, 10, 12. Now I'm at 12 electrons. I still need to get down to 10. So again, I'm going to pick this one and this one. They're going to get knocked off, and we're going to make that into a triple bond. And this is how you would go about drawing them out. You always want to draw them with one bond between each element. Make sure everybody has the octet rule. count, and then you want to try to make sure that you have the correct number of valence electrons. So 2, 4, 6, 8, 10. That's right. All right. Hopefully this has been a good overview for you guys on bonding. And if you have any questions, let me know. And I look forward to seeing you guys on the Google Meets or in person next